Got it? I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless our time together, that you be glorified in what we do, Lord. In your name I pray. Amen. Okay, so, I'm battling with myself, like, what should I do today? So I finally basically come to odds and ends. And so this is going to be an assortment of things that I could have said at other points, but I think it's good that we say them now. So first thing I would point out is the first isomorphism theorem. What was it? We have a homomorphism, right? From a group G to a group H. And what did the first homomorphism? So what did that then what? Then we get that G mod the kernel of phi is what? Is isomorphic to what? Phi of what? Phi of G, right? Or the image of phi, if you like. I guess I have to admit something, guys. And this hurts me, like, a lot. Because, well, anyway, you maybe want a symbol for homomorphic, right? What? 3 squiggly bars? So I have to admit, guys, that I have been wrong. And it pains me to do that. But I really should be writing this here, right? Or perhaps this symbol, I mean, for isomorphic. I don't know. Do you guys want to change it at this point? Or you want me to just stick with squiggle for isomorphic for here? Stick with the squiggle for isomorphic? All right, well, we're too far in? All right. So what do you guys want to use to denote homomorphic? H above the squiggly line? Okay. All right. What's that?
Was what we were using for isomorphism supposed to be?
Well, I mean, you could do whatever you want. I mean, if you want, you could put a Pac-Man here, and it would still be legit. But then you're going to have a hard time talking to people. They'll think you're crazy, you know. And in the same sense, if you try to read other books, you'll be like, why don't they talk about the Pac-Man between sets? It's so weird. But I'm just warning you. In many books, what I've been using as this, right, is translated into either this or some other symbol, right? I don't know. Homomorphism doesn't come up that much, but maybe homomorphism would be the double squiggle or something, or I don't know, or maybe let's not get into it. So we have decided we're going to stick with this as isomorphism. And if homomorphism comes up, we'll invent a symbol if we need to have one. All right.
And so what is the symbol for homomorphism?
I don't know if I remember it. What did you? I mean, did we give a symbol for it? I don't remember. Did we? I mean, I can look up my lecture on homomorphism and see what I said there. This was not the point of this discussion. I have chased my own rabbit. All right. I mean, I invented the rabbit. I constructed it from simple rabbit bits, and we didn't have a symbol. What lecture was that? Lecture 10.
Is homomorphic too.
Okay. I've gone to the trouble of my computer. I have to look at it myself. It's just my OCD. Let's see here. Not that I really believe in that sort of thing, as it's some sort of psychological construct. Yeah, I said isomorphic G squiggle G bar, but I did not say what it means for two groups to be homomorphic. Yeah. But I think a reasonable notation probably would be that I should use this for homomorphism and that with a bar under it for isomorphism.
Just going back and studying all
That's what I'll do next year. Or the year after, whenever I teach it again. All right. Perhaps never. I don't know. Let's see here. You could be the only ones. I don't know. Let's see here. All right. So this is the first isomorphism theorem, right? Now, if G is a finite group, then what? So let's see here, some observations. If G is less than infinity, right, if it's a finite group, then what do we have to say in terms of the size of things or cardinality? What's the size of G mod the kernel? Is what? Remember, the number of cosets, the number of kernel phi cosets of G is what? It's the order of G divided by the size of the kernel, right? It's part of Lagrange's theorem, I suppose. And on the other hand, that's equal to what? That's equal to the size of the image, right? Cardinality of the image of phi, if you like. So we have this relation. The order of G, right, is equal to the size of the kernel times the size of the image, right? So when I read this comment in Dummett and Foote the other day, it confused me momentarily because he said this is really just the rank nullity theorem from linear algebra. So what does he mean by that? This is just the rank nullity theorem. First of all, what is the rank nullity theorem from linear algebra? Let me state it for linear transformations, all right? There's a couple different forms of it, but if we have T, right? If we have T, a linear transformation from vector space V to vector space W, then what does the rank nullity theorem say? It says the dimension of V is equal to the dimension of the kernel of T, all right, plus the dimension of the rank of T. Or sometimes this is replaced with, I guess I should, fine. Let me state it in a way which makes it more interesting. Hold on a second here. So rank nullity. So it is the nullity of T plus the rank of T there. Now what are the nullity and the rank? The nullity, nu of T, is the dimension of the kernel. What's the rank of T? It's the dimension of the image of T. Right? So how is it? What does Dummett and Foote mean? Or I guess I should say Dummett or Foote. Or is it Dummett and Foote? I don't know. Did they write the whole textbook together? Or it's two different people. It's not like there's some guy named Dummett Foote. Although that would be a pretty killer name. We're expecting our fifth in February. It's a boy. So we're trying to find names right now. We have many ideas. My children have suggested Xavier, which I will admit I'm attracted to, but it's a somewhat abiblical name. Dummett and Foote. That's funny. I'll have to tell my wife on that one. Then I have a friend named Stephanie. She's like, you should name him Stephen, and that's not just because it's the male form of Stephanie. Like, So I don't know. We have no idea yet. I've already got their names already assembled HDMI, so I've got that sort of like nice way to remember their names. I'm not like, do you know some 5-letter abbreviation that has HDM and I in it? They could add. It's like some special kind of, see, I don't know.
Had me.
What's that?
Had me.
Had me?
Yeah, with the respelling.
See, I don't know. I'm not sold on anything yet, but do you see? I mean, so when you look at these two things, on first glance, they really don't look at all related, do they? But keep in mind, these are vastly different worlds you're looking at. Here we're talking about finite groups, right? These are actual numbers. These are integers. And over here, well, these are also numbers, right? But the thing is, V and W are what? These are infinite abelian groups. I'm assuming that we're working over, F with characteristic 0. And what that means basically, let me be less opaque. I'm saying F is equal to the reals, or the complexes pretty much, or possibly the rational numbers. All right, it's an infinite field. So these are infinite abelian groups, all right? So what does he mean when he says it's the same theorem? How about this, though? If you look at what is, excuse me, what is the first isomorphism theorem then say about this linear transformation? It says that V mod the kernel of T is isomorphic to what? The image of T, right? Is the first isomorphism theorem only for finite groups? No. This is a general theorem that holds for infinite groups just as well as finite groups. Which, by the way, is why part B of your homework made no sense. But anyway, more about that tomorrow. Yeah, there's that 3-part homework. I think part B was not legit. Let me shut up about it. Tomorrow, I'll talk about it tomorrow. So, I will post my solution later today. I have like 3 more homework solutions to post for you guys, but tomorrow I'll talk about them. Okay, so then what is the relation of the dimension of a quotient space in linear algebra? Do you guys know how that works? What's a quotient vector space? Well, if you had my linear algebra, you talked about this. We spent some time on it. But if you had somebody else's, maybe you didn't. So here is an example. If you're in R3, right, you can look at R3 as R3 mod the, say, xy plane. Right? So then what that means, this quotient space is things like what? It's things like basically a point plus the xy plane. I really should just come up with a name for this stupid xy plane. Like, let me call it P. Right, so, oh, bad choice. Yeah, I see why Mr. Hoogerworth was amused. He saw what was going to happen to me. Let's call it M. There. So anyway, you can picture them here, of course, right? They're just horizontal planes, right? And which plane you're on is completely fixed by where you are. Here is P itself down here. Excuse me, M. I'll get it on my system eventually. There's, and so you have this stack of planes, right? 2-dimensional planes, and they fill up all of 3 dimensions, right? So you've got this chopping of the 3-dimensional space into this disjoint family of planes. These are the left additive cosets of the xy subspace, right? That does gel with our discussion of cosets this semester. Our discussion of cosets, well, parts of it were finite, other parts of it were infinite. I mean, the fact that if you have a group multiplication and you have a subgroup, that cosets of the subgroup partition the space, that's true even when the group is infinite. What you lose is the ability to count in the same way for infinite sets. Like finite sets, we were able to use counting to get things like Lagrange's theorem, right? But obviously you can't count the number of points in R3. But you can still make legitimate comments about dimension, right? Dimension of infinite spaces is still finite. That's the beauty of dimension. It captures a certain finiteness about these infinite dimensional spaces. And there's a very simple relation here. So this family of planes really is what? It's really, you can see it's the same as just the z-axis, isn't it? Right, there's a natural correspondence between this and just the point P. And you could use the point P as 0, 0P without, if you like. I mean, it's just the intersection point that indexes which coset you're in, right? What I'm trying to say is that R3 mod the xy plane is really just R again. But geometrically, I think of that R as the z-axis. What's the relation between dimension of the quotient space and the space you're quotienting by? It's pretty clear, right? The dimension of the quotient, R3 by M, is what? It's 3 minus the dimension of M, isn't it? Which is 3 minus 2, which is 1. So in linear algebra, the dimension of the quotient is not the dimension of the thing you're forming quotients in divided by the cardinality. What are you doing? Oh, okay. I look back there, I see Lorenzo lifting up the camera. I'm like, what? It is a new kind of camera work. I have not seen that before. But which animal did you learn that from? Oh, okay. Yeah, sorry, I forgot. You're like a vocational dispensationalist. You divide your math into math and your zoology into zoology, and never the two shall meet. But I've already shown that this worldview is false with my examples of leg counting. Sorry, I actually do have things to say today. Let me stop wasting the time. Dimension of V mod the kernel is dimension of V. And I prove this in linear, whether you like it or not. I mean, well, anyway. So there's why it's the same theorem. It's because the dimension of the quotient of a vector space is not defined by dimension of V divided by the dimension of kernel T. That's not how it works. Dimension is not cardinality, right? Dimension is something else. It's the number of vectors you need in a linearly independent spanning set to get the space back again, right? But that is one of the fundamental confusions of abstract mathematics, especially for students starting, is confusion between the concept of cardinality and the concept of dimension, right? A vector space has infinite cardinality, but it has finite dimension. Possibly. I mean, we can also talk about vector spaces with infinite dimension, but we don't do that too much. Anyway, so as you can see, then dimension of V is equal to the dimension of the kernel plus the dimension of the image, which is nullity plus rank. That's the rank nullity theorem. They really are the same theorem, with the understanding that the dimension of a quotient space is the difference of the dimension of the superspace and the subspace by which you're quotienting. So there's one comment. Are you happy I got this out of my system? Now it's less likely as a test question.
Yes.
Okay. You don't think it would have been fun to discover your confusion about these issues on the test? No? You remembered it then, though, right? No? All right. All right. Now for something completely different. An example. I'm still waiting to get a copy of Dr. Sprano's notes because I want to give you example. I wanted to pick some of his bizarro groups that he has in his notes and see if we can't figure out what they are. But the students who promised to give me these notes have never delivered, so I don't have the examples yet. And yeah, oh well. I know, right? Why didn't I use Dr. Sprano? That's a good question. I don't know. I don't really have a good reason for that, but I already know that the students claimed to already have them, and they were going to bring them to me, so I just, yeah, trusted. I see where I went wrong. I trusted students to do something. Yes, that was a mistake, wasn't it? Let's see here. Yes, your argument is very powerful. Let's see here. So here's an example. Let X be a set. All right. And suppose A and B are subsets of X. You can define the symmetric difference of A and B by A plus B. And what that is A minus B unioned with B minus A. All right. So this, if we let, so basically, well, here's the notation that Rotman uses for it is this. B of X basically is, well, here I would say it's the power set of X paired with symmetric difference. So the power set of X is what? All subsets of X, right? So the set of all subsets of X is the so-called power set of X. So I'm claiming that this, if you take two things, two subsets of X, you can add them, all right, by this symmetric difference operation, and it gives you a group operation. This is the so-called Boolean group. Oops. Boolean group. I think, was it the Boolean group on? He just says Boolean group. Named after the logician G. Boole, 1815 to 1864. This is old. Let's see here. Let me draw some pictures for this symmetric difference. It's kind of fun. This was one of those things I've been trying to work it into your homework. It just never quite happened. It's been on my list of things to do. Just got word left out. But so I think this is easily shown. So here's A. Here's B. All right. So where's the symmetric difference? So let's see here. A removing B is what? It's this piece, right? And then what is B with A removed? That's the other, that's this piece here, right? That's this guy. So excuse me. So what would serve as the identity here? So let's try to think about this. What's the identity? Let's see if we can figure that out. We want A plus B to equal to, well, I'm sorry, we want A plus B to equal to A again, right? And we want that also equal to B plus A, right? Maybe let me call it E, so it's less weird to you guys. So what should the identity be, being that we're defining this operation, A is a subset, right? We need A and E subsets of X, or AKA A and E elements of the power set of X. Would an empty set work? Would you guys agree? If we take So let's see, A with the empty set removed is just A again, right? And then if you take the empty set and you remove A, it's still the empty set. So A union the empty set is just A again. I think we have a winner. So yes. So apparently, the empty set, E is equal to the empty set. So we have an identity. All right. How about inverse? There we're looking for A plus B to equal to the empty set and also to be equal to B plus A, right? That would say that B is the, let's say, inverse of A under this group operation. As a matter of common decency, this had better be a commutative operation. Otherwise, this using plus is really not cool, with me anyway. What'd you say, A again? Yeah, I think you're right. If we take A minus A, we get the empty set. And then over here, we have, again, right, empty set union empty set is empty set. So yeah. So that implies that B is in fact equal to, B is equal to A again. Or if you like, minus A is equal to A. That's our notation for the inverse in an additive group is minus A, right? So this is, we might say A inverse equals to A in multiplicative setting. But here we're in the additive setting, so we'd say minus A is equal to A. Is it commutative? I should have taken a second to notice that earlier, right? I mean, you can see that from this expression, right? The union of set 1 and set 2 is the same as the union of set 2 and set 1, right? So because these are interchangeable, that means that A plus B is equal to B plus A. It's clearly an abelian, and a commutative operation. So what's left? Associative, right? Yeah. And so he proves that with a picture. Let's see here. Well, I mean, it's proved in our homework earlier, but the associativity involves see here. See if I can do it right. Oh, I always butcher this stupid thing. Oh, well. All right, so this be A, B, and C. So let's work it out geometrically. So what would let's say A plus B be? This piece, right? There's A plus B. Then what's plus C? So A plus B plus C, the symmetric difference of what I already have with C leaves me what? It leaves me this down here, right? And what do I lose from what I already had? Right, so I got to get rid of these, right? Do I gain anything else? No, I don't. No, I just that's it. I can't pick back up this, right? I don't pick this back up. Do I? No. So there's in green I think, if I've done this right. If you guys, well, we'll find out if I'm doing it right shortly. Yes?
Why don't you pick that up?
That's what I'm wondering. Should I pick up that middle trinket? I do? Let me think about it. A plus, so this is going to be equal to what? This is equal to A plus B with C removed, unioned with C minus A plus B, right? By definition, that's what this is, right? So A plus B removing C
The second one will have the center.
so first of all, where is this? A plus B removing C is what I have up here, right? It's the top of the overlapping Mickey ears. And then C less A plus B, you're right, that does, we do get this, don't we? Thank you. All right. Right. See, these points are in C, but they're not in A plus B, so that's why we pick them up from over here. How about on the other hand, B plus C? Well, B plus C is what? B plus C is it's this and that, right? That's B plus C. And then if I do A plus B plus C, what's that give me? First of all, I do A plus, so I lose these pieces, right? And I pick up this, well, excuse me, I pick up this piece over here, right? And then again, I pick up the middle piece because that's in A, but it's not in B plus C. So, as you can see, it's the same set. Consequently, these, if you'll allow me one of these kinds of equals, should save me some writing, are equal. So that's associativity of the symmetric difference operation. That could have been one of your homeworks. I guess that would have been a fun one, though, if I'd put the picture in.
Yeah.
Yeah.
See, the picture is in Rotman. He's a kind soul. Actually, that's an earlier homework, and then he later gives the Boolean group example. All right. Excuse me. Anyway, there are many other examples of groups that we haven't gone over. It's just an example of a Boolean group. You can see every non-zero element, except for the identity, has what? What's its order? What's this say? 2A equals to the empty set, right? In other words, every element has order 2, except for the identity. So if you look at the Boolean group on 2 elements, you can ask what's it isomorphic to. What would this be isomorphic to? How big is the power set? Right? So this is what? This is a group of order what? 2 to the 2, which is equal to 4. It's a group of order 4 in which every element except for the identity has order 2. We already know this. This is the Klein 4 group. It's C2 cross C2. Just recast in the somewhat weird language of looking at the symmetric difference on subsets of 1, 2. If you look at the Boolean group of 1, 2, 3, you've got power subsets of 1, 2, 3. There are 8 of those, and then you'd have a group of order 8 where every element except for the identity had order 2. What would that be? It's Z2 cross Z2 cross Z2, right? Z2 cross Z2 cross Z2 is a group of order 8 in which every element has order 2 except for the identity. Yeah. That we have not talked about as much, so it shouldn't be familiar to you, but if you think about it for a little bit, it'll become obvious. The empty set. Yeah. Another example of a group. Well, no, I think I better stop there. We could keep. There are many more examples, but that's a good place to stop here. I have a handout for you. So for the last 10 minutes of class, I want to talk about this handout with you. And this is sort of the next thing in the counting story. This is it's known as Burnside's lemma. This handout is again taken from Rotman, and I want to talk through the proof of Burnside's lemma with you here without too much writing. I mean, left to my own devices, I would spend 20, 30 minutes carefully going through this proof, and I would enjoy it very, very much. And you might enjoy it. I don't know. Depends on how stressful your week is and so forth. So I will spare you that. I'll just talk about the proof with you. Sure. Thanks for asking. Let's see here. So Burnside's lemma says the following. Well, actually, there's two other. There's a little bit before this I need to write on the board because I didn't copy this part of it. But these actually make really nice little test questions. What page are we on? 209. All right, so these are actually really pretty. Lemma. This is lemma 2.159 in Rotman. Anyway, 1, if G is a group, so Rotman likes to use big X for his set. We use a capital S for this mostly. All right. If X is an element of big X and sigma is an element of the group, then the stabilizer of sigma X is equal to the conjugate subgroup to the stabilizer of X by sigma. And then 2, and I think we've proved this previously, is that if X and Y are elements of the orbit of X, then the stabilizer of Y has the same size as the stabilizer of X. All right, anyway. All right, just need to. I'm not going to prove those, but we need those to understand the thing we're reading through here. So, excuse me. And I guess I should actually write Burnside's lemma here. So here's the lemma theorem. It says let G act on finite set X. Then if N is the number of orbits, then N is equal to 1 over the size of the group, G, times the sum over tau and G, f of tau, where f of tau equals number of x in x fixed by tau. So this is Burnside's lemma. So let's look through the proof here, try to understand it. So what he does is he says you list the elements of the set, right? x1. First of all, pick x1, all right, and then you list all the things in the orbit of x1. Let's say x1, x2, xr. That's the orbit of x1. He says then you pick xr plus 1, which is not in the element of the orbit of x1, and then you list the orbits of our xr plus rx plus 1, xr sub. I can't say it. X sub r plus 1, x sub r plus 2. Basically, he's saying take the elements of the finite set, right, and group them by orbits. The first orbit, then the second orbit, then the third orbit, and so forth, all right? Arrange them orbit after orbit after orbit. We know that the orbits are non-intersecting from our previous study of group actions, right? So they partition the set X. And then he says make this table, and he either puts a 1 or a 0. He puts a 1. The table has the elements in the, I can't write. I should not write. The reason I gave this is so I don't write this. So the table, right, we're looking at on page 209, he puts the elements in the set in the top, and then the elements in the group, which is acting on the set in the first column, right? And he either puts a 1 or a 0 in each spot in the table, depending on whether the permutation tau, the group element tau, fixes x sub j or whether it moves x sub j in the group action, right? So every group element either moves or doesn't move the given points in the set, right? Okay. And so what he points out is that the number f sub tau I, the number of x in the set which are fixed by tau I are what? It's the number of ones in the ith row of the array. So the sum over the group element of f of tau is the total number of ones. So if you think about it, if you look at the whole table, the sum of all the ones in the table is this sum. But then he points out that if you look at the number of ones in the first column that fix tau sub I, the number of ones in the first column is the number of the tau sub I which fix x1. All right, well, what does it mean for the group element to fix x1? That means it's in the stabilizer of x1, right? So the first, oh no, I got so far without doing that. So the number of ones in the first column is is the size of the stabilizer of x1. The number of ones in column 2 is the size of the stabilizer of x2, and so forth, right? So, but how many things are in but of course, as you're looking at it, how many things are in the stabilizers in the same orbit, right? They have the same size, right? By this lemma, the size of the stabilizer of y is the same as the size of the stabilizer of x. So if you look at it, for example, the first r columns that correspond to the orbit of x1, that would give you, as he explains here, r times the stabilizer of g1, but then by the orbit stabilizer, we can convert that to the size of g, right? Because the size of the orbit of x1 is the size of the group divided by the size of the stabilizer by the orbit stabilizer theorem. And so then the size of the stabilizer cancels, and you just get r times, you see the equation at the bottom of the first page of the handout. So you can do that for each orbit, right? So the number of orbits times the order of G then is equal to the number of ones in the whole thing, which the number of ones in the whole thing is a sum. So you got n times the order of G is equal to the sum, and there's the theorem. I'm sorry if I haven't made sense. I mean, if we spent 20 minutes sorting through it, it's actually not that complicated. It's pretty easy to follow his proof, honestly. I have found more clever, snazzier proofs in other books that just made me go, what? But it's a kind of low-tech proof, but it's a good one. The application here is really what I brought this here to you for, though. Now he explains how to use this lemma to solve an interesting problem. So suppose you're trying to count the number of flags that you can make with 6 stripes, right? So do you understand so you got this flag. It's got one, 2, 3, 4, 5, 6. These are supposed to be, the same. These are supposed to be equivalent. If these would all be squares or the same size rectangles if I did this right? And he says each one of these segments in the flag, you've got 3 colors to choose from to color the flag. All right. And the reason I'm drawing 2 is like the example he gives. He's like, suppose you have red, white, blue, red, white, blue. If that's the front side of the flag, if you're looking at the back side of the flag, what would it look like? Right. Blue, white, red, blue, white, red. So we should count both of these as being the same flag. All right. So here's the set. He looks at the set X equal to all 6 tuples of color. All 6 tuples of color, red, white, or blue. Right? And what's the group that acts? The group that he has in mind is a two-element group. It's just 1 and tau, where tau is just this. Tau is the fact that you can look at the flag one side or the other. And so then if you read through this, he explains, first of all, the identity permutation, right? That fixes every element of the set. So f of 1 is just 3 to the 6th. But on the other hand, f of tau, he argues, is, 3 to the 3rd, because, well, I'll let you read the details here, but basically he argues that the number of such flags is 378, and it's just from using this formula here. And to answer your question, Nathan, no, I wouldn't put this on the test because I'm kind of hurrying through this, and I think it's significantly more complicated than the counting examples we've done so far. I want you to be aware of it. And if you're interested in this kind of counting by group theory, you should read this section in Rotman and study further. There's deeper things in there too. There's this theorem by Polya and so forth that are a little bit more complicated. Now, some of you who have studied combinatorics or maybe discrete math, do you guys do this kind of thing in there? Do you do these kind of counting problems in anything that we have here? I don't know. In discrete, some counting, yeah.
Some kind of similar.
But if you really understand this theorem, it allows you to do counting that would be very difficult otherwise. I'll shut up.